you to actually get or develop a good understanding of the nature of lines and planes in three-dimensional space visually, right? Because linear algebra, I mean, we talk about the mechanics of it, where we row reduce matrices and operate on matrices and things like that, but it's very easy to lose sight of why are we doing that? You know, what is the end game? What is the whole objective? Why? Just why? You know? So Geogebra is a pretty useful resource when it comes to that. I know some people are more familiar with Desmos, and Desmos is a good resource too, but what I've come to understand, and maybe it's just because I don't know Desmos as well as I know Geogebra, in my experience, and if you know better than I do, please, I'm all ears, just not right now, because this is all typed up and everything, so like I'm not going to change it to Desmos just yet, but like after class or something, if you know how this works on Desmos and you can explain it to me, because I do know that Desmos is a lot less glitchy than Geogebra, but from my understanding, the 3D stuff works better on Geogebra, or at least it has more functionality. All right, so you're going to start off pretty much where you left off last time in that Google Doc. All right, there's a section for Tech Assignment B. That's where the links to this are going to go. But the line commands are what they are. You know, if you can copy and paste it and put it in, by all means, go for it. But that was weird. I don't even know what I hit to make it zoom like that. Because I just hit shift and, no, I'm just curious now. Hold on, shift. I must have hit, I don't even know what I hit. It zoomed, I hit shift and 9 to open parentheses, and it started zooming on that. I just wondered if I learned, like, accidentally a little shortcut key. That would have been pretty cool. Or maybe I tried hitting shift A. I'm gonna hit shift everything now. Nothing's working. Maybe I just accidentally rolled it or something. So A equals, I personally, I like to put the identifier in, the variable that we're letting the ordered triple in this case be equal to, just because I don't want to lose sight of it, right? Because sometimes, you know, you're pointing to a particular value, and it's easy to lose sight of, you know, what it should be pointing to based on what you've already typed in. All right, so 2, -1, 1. U equals vector A. So this part should be familiar. V equals vector B. I used to teach some of my courses here in one of the computer labs. That was great, because then everybody's following along at the same time. It was, oh man, it was perfect. All right. So curve. So I put a little notation here so that you could actually learn a little bit about why these things work the way they do. This is actually the parametric form of a line in 3 dimensions. All right, so there's 3 components. 1 plus t would be the x component. So that would be the linear function in the x direction. 2 minus 3t would be the linear function in the y direction. And 3 minus 2t would be the linear function in the z direction. All right, so all of those put together gives you a line that is basically omnidirectional. You're looking at something that's going to go in all different directions, so x, y, or z. So curve, and it'll identify the curve in a way that makes sense to GeoGebra. So you just type curve, you can capitalize or not, it doesn't make a difference. 1 plus t, 2 minus 3t, 3 minus 2t, comma t, you have to define the variable, bless you. You have to define the variable, so you have to let GeoGebra know that the variable is t, because it has no problem whatsoever working with a variety of different constants. So I could represent this curve with A, B, C, D, well, any letter you could possibly think of. But then once I designate t as the variable, everything else takes on the form of a constant. All right, so it's just some static numerical value. So Negative 10 is the lower bound. Positive 10 is the upper bound. It really doesn't matter what the lower and upper bounds are, because I'm just trying to give GeoGebra a place to start and stop with the graph. I mean, I could do negative 100 to 100. I can do negative 1,000 to 1,000. I can do negative 2 to 2. It's just how much of the line do I want to see. You can see it already plotted it on the graph, but I want to hit enter to lock it in. All right, and you could see that it's in the parametric form. All right, and so just not, not to sound too vocabulary-ish, like, because parametric equations is technically a Calc 3 topic, but we're in the portion of linear algebra where there's a significant amount of overlap between Calc 3 and linear algebra. All right, so parametric equations, we actually spend a lot of time in the early parts of Calc 3 talking about what those are and why they work the way they do and how to graph them. For our purposes, I really just want you to get a sense of what they look like in space, but all you really need to know is that you're redefining x, y, and z in terms of a new variable, in this case t. T typically represents time. It doesn't always have to represent time. You could parameterize an equation any way you want. Like, you can parameterize in terms of radius if you're dealing with a circular function, or arc length, or height above the ground, right? Age, which is a measure of time, but still, but in a different capacity. So you can rewrite your function, if you're just thinking in two space, y equals x, you could rewrite it so that you introduce a parameter of time. Because y equals x is just a line, but how are you moving along that line? That's what the parameter will tell you. All right. So I can move this around, and you can see there's definitely a line in space. All right. And it's being essentially, you can really kind of think of it as being sort of supported or held up by vectors u and v. All right. To some extent, anyway. All right, so what I want to do is, personally, I don't want to be just limited to this particular parametric function. Yeah, I created a line in space. That's wonderful. I want a command that's going to give me any line in space. All right, so that's where I'm going to go now. All right, so my line command, I really feel like this is probably a typo because I've used A for something else. Well, we're going to find out, because it's going to either let me call it A or not let me call it A. All right, so x sub O. Now, we need subscript, so that's when you got to kind of get creative here. If you kind of scroll around through all the different options here, under f of x, you could see one that says subscript. Well, it doesn't say subscript, but it looks like a value with a subscript. All right, so you would just type in the x and then the 0. All right. The screen brightness is not making it easy to see, but on your computers, you'll probably much more easily be able to see it. All right, so y sub O sub 0, and then z sub 0. So you hit enter, and I guess they updated it since I wrote up these instructions, because it just flat out made the sliders for you. That was great. Because normally it would bring up, anytime you put in a constant, it would bring up an option to create sliders, but it looks like they programmed a little common sense into GeoGebra so that it knows, well, you put a constant in, so clearly you want a slider. All right, now you, as if you don't have any experience with this, you'd be like, well, why would it know to do that? Why would that be important? The constant is something that you want to have control over. Right? So by creating sliders, you're able to manipulate that constant very quickly and easily, rather than actually replacing the x sub 0 with a 1, then a 2, then a 3, then a 10, whatever, and watching it change like you would on a graphing calculator. It's like, I want to graph y equals 2x squared. All right, so go back in to y equals, change the 1 to a 2, All right, I want 1/2 x squared, so make it a 0.5. You got to go back in every time. Now, it's still better than doing it all by hand, but if you had a slider, you know, imagine your graphing calculators were touchscreen, and you had, or even a touch pad, where you could just manipulate that coefficient just by sliding it back and forth and just seeing the width of the parabola change. Wouldn't that be more effective? GeoGebra is going to do the job for us, right? So I can slide this puppy here, and it's going to move my point in space along the x-axis, y-axis, and then eventually the z-axis once I get around to it. All right. So I'm going to create a vector going to coordinate ABC. All right. So, you see that it's definitely a typo because I reuse these. You know what? I know what happened. I did it all on here, and I didn't pay attention to what it was being called in here, and I just said, oh yeah, just let it be A and U. I just copied and pasted from up here, and I just edited it. This can't be A, I already used A. This can't be U, I've already used U. But what you can do, well, first, submit it for typo bonus. Then second, just type in the coordinate and let GeoGebra define it. All right, so the next one would be vector, double paren ABC. Hit enter. Doesn't seem to want to let me do. I think I do have to define it. So W. All right. Workaround. A comma B comma C. Did I use A, B, and C already? Lowercase. I don't think I did. Oh, there they are. So I must have used A somewhere along the lines. It defined my curve as A. That sneaky son of a gun. All right, so let me call that Q or something. All right, so there's another typo for you. It's a really good thing I'm going through this. Well, if we call that Q, let me just wipe this out and these sliders, and I'll just do it again. Now I shouldn't have any kind of contradiction. So vector A comma B comma C. I just experienced some serious deja vu. I feel like I've definitely been down this road before. But clearly nobody submitted it for typo bonus, otherwise I wouldn't be experiencing said deja vu. All right, so we want to define this curve. Which one was it? It was the first curve. And the race is on. All right, so this curve up here, that should be Q equals or something, basically something other than A. And then this should be C equals. All right. And so if those typos come in forthwith, then somehow between today and tomorrow evening, because I have tomorrow off, I should be able to make those edits and have the revised version up there, so you should have the most accurate one to work with. All right, so now I have a vector when I'm sliding it around that's on the move. All right, so some good stuff going on there. So I want to have a curve that's plotted in general terms. All right, so my curve here, now this one I think I can call it whatever I want because it's the last step. All right, so curve. The only thing is you have to write it in general terms. So basically what you see there is what has to go into GeoGebra, including the subscripts, which are kind of a pain. But you can copy and paste. It's just if you're anything like me, you copy, you paste, and then you forget to do the edits along the way. So that could be troublesome. So let me see if I can do that. And then that help thing, I don't know why that comes up for so long. I know it wants you to like read it and everything, but and there's no reason why it should be up that long. So just pop it in, plus BT. Oh, no need for a space. CT, and then comma T, comma -10, -10, comma 10. All right, so it defined it as a new curve, the curve D. But again, now it's defined based on the parameters that we established, A and so on. So I can bring it out a little bit, move it around, and you can see now I have a second line that is dependent on that vector. That vector is known as the parallel vector. So lines and planes are dependent on what or how they relate to a particular vector. All right. So for lines, we want a parallel vector. For planes, we want something called a normal vector. All right. So bottom line is we need a vector to base our equation off of. And so this shows how to do that. Now, your picture might be a little messy, and you'd say, oh, I didn't need to scroll that up. Maybe you're like, it's too messy. Let me get rid of some of this stuff. Maybe you just want to look at the one that's got all the sliders. I'll even get rid of these other points. Click them off, and then look. And now you're just comparing the vector and the curve itself. So now when I slide some things around, you can see what's going on here. So the point is really just dictating the position of the line compared to, well, this one's not showing much of anything because the way I have it oriented, but if I change the orientation, you can see that it was really moving. It's just not from our perspective. Then I could play around with my vector, and you could see as the vector moves, so does the line. So these are some terms that I'm going to be talking about later. It's nice to have a visual to go along with the words that I'm just going to be hand waving through. All right. So then once you do that, you're going to save. Save it as something that's not this. So this would be line, parametric line, or something, whatever. Parametric line. Save it. Oh, I never signed in, but whatever. I have like 30 of these already, so I'm good. But then once you do that, click share. But now I do have to sign in. I don't have a choice. Okay, so this is no secret. All right, so now I'm going to save it. I'm going to keep it on private so nobody steals my work. Been down that road before. Copy this. This is the link that goes into your Google Doc. All right, so then once you do that, new, now we move on to the plane. Plane's a lot easier. I mean, you could even see the line commands are really not much of anything. All right, so AX, let me get rid of it. I just think it looks ugly. The XY plane, it shows like some bland gray. It's just not appealing, so I got rid of it. All right, so this is the equation of a plane in its most general form. When I graph it, it was like, oh, well, that doesn't look like much of a plane. But then when I turn it, it's like, oh, there it is. All right, you're just getting the side view of it. When that happens, everything looks like a line, I guess, or at least the planes go. But then I can manipulate the A value and get a sense of the orientation of the plane based off of that, or those coefficients. All right. So every coefficient represents something. So it's just a matter of what do those coefficients represent. And this click slider thing, normally I would say, based on the experience here, I would say, well, that's a typo, let's get rid of it. But I'm nervous about that because I'll get rid of it, and then next week you'll have to click slider in order to get all this stuff. So I'm just going to leave that one. All right, the next line command would be vector ABC. And you're like, what ABC? Well, the ABC that was created based off of your plane equation. So vector, so it's just going to call back to the same sliders. I I forgot to open set of parentheses. Now I gotta wait a half hour for this to go away. There it is. Yeah, it's parentheses for the command and then parentheses for the ordered pair. Or ordered triple, sorry. So now I have a vector. Now you can see that this vector appears to be, if I look at this as kind of a two-dimensional rendering, all right? So I'm looking at the side view of the plane. This looks an awful lot like a perpendicular relationship, all right? That term perpendicular really only deals with linear functions, so in two-dimensional space. So we go with orthogonal, all right? But we'll elaborate on that a little bit more, all right? Then we could also create another plane, fx plus gy plus hz. Really doesn't matter as long as your coefficients are unique to this plane. Hit enter, it creates the sliders for that. Do the same thing with the vector. So I want the orthogonal vector for both planes, because I not only want to see how the planes relate to one another, I want to see how their orthogonal vectors relate to one another. All right, and so you could play around with orientation, you could play around with coefficients, and see what's going on. All right. Another thing that Geogebra will do for you, it's a really wonderful thing, it'll compute the intersection between planes. Now the intersection is going to be a path. That path is a linear path. All right. I have it pointing to E and I, but my planes here are P and Q. All right. So when I did this the last time, they were E and I. So intersect path. Plane and plane is going to be P comma Q. All right, so you got to make the adjustment based on your own setup here. All right, and so you can see that little blue, well, not little, but that blue line represents a linear path between those two planes. So those two planes intersect one another, and it creates a linear function, all right, in 3 space. All right. Now that linear function is actually represented, yeah, and I actually made shockingly, I made a notation here. My planes are designated as E and I, your planes may be called something else. All right, so in this case it's P and Q. So when I come up with my solution, you know, it might not be in a form that is familiar to you, but you know, you see this lambda notation. We're going to get to that later in the course and what that really means. But generally what we're talking about is the transition to something known as an eigenvalue. All right, so we'll get there, but for now it's just a way of representing the intersection between two planes. All right, so after you do that, you're going to find the intersection between these two particular planes. You don't have to do anything unique. Just go back and change your sliders so that they correspond with these values. Little tip, because I've seen people like, I can't quite get the 2, I keep going. Just click on the number and change it up here. You know, what is it supposed to be, a 2? Just change it to a 2 and then hit enter. It'll move it for you. All right, just save yourself the heartache of like, I can't quite get it to be equal to, oh, that time, and then it went off. Change it up here and it'll orient itself correctly. All right, but the little follow-up questions here, what's the relationship between two planes when their normal vectors point in the same direction? All right, normal vectors are the same thing as orthogonal to the plane. All right, so these two black vectors are the normal vectors. So I would just want to know, if those were pointing in the same direction, what would be the relationship between the two planes? All right, well, I have no idea. So let's move it around until they're pointing in the same direction. It might take a little doing. I mean, I suppose you could also Google it, but where's the fun in that? You know, the exploration part is the big thing. That's where the learning's going to happen. So I recommend you do that. But there are 3 questions, and each one of them has a very straightforward, distinct result. All right. So I'm not looking for an essay here. I'm just looking for it's this, it's that, and it's the other thing, you know, like very simple. Just always keep in mind when you're writing answers to these kind of questions, I do not have much of an attention span. So just keep it simple for me, all right? If everything in literature was written by bullet points, I would be the happiest person in the world, all right? So there we go. Anyway, so that's your tech assignment. Due in whatever I put in the calendar, 2 weeks, 3 weeks? 2 weeks probably. It's usually 2 weeks. That's why I put it on the calendar, because I can't count on myself to remember. All right. I feel like it's Windows Shift Q. I'm going to go for it. Windows